So if you take an electron, right, and you somehow manage to trap it inside an atomic nucleus, it doesn't just, sit there quietly.
No, definitely not. It doesn't become this neat little package at all.
Right. Instead, its energy just spikes. I mean,
Yeah.
so violently and incomprehensibly fast that it would literally blow the atom apart from the inside out,
Yeah, it would completely shred the fundamental building blocks of matter.
which is just wild to think about.
It really is. I mean, it mathematically proves why the universe has to be mostly empty space. If you squeeze the fabric of reality too tightly, it pushes back with an impossible amount of force.
And that is the level of profound structural reality we are dealing with today. So if you are joining us, you are probably gearing up for a major high-stakes physics exam.
Which is incredibly stressful, I know.
Oh, absolutely. You're staring down a syllabus packed with quantum mechanics and wave optics, and it honestly probably feels like this terrifying landscape of diagnostic muddy waters.
Yeah, a lot of students just see a wall of math.
Exactly. But today, we aren't just memorizing a list of physics formulas. We are looking at the mathematical source code of the universe. We want to show you exactly how to dismantle the hardest, most deceptive questions your professor is going to throw at you.
Because honestly, the biggest mistake students make is treating these formulas like black boxes.
Right, like you just punch numbers into a calculator and pray the right answer falls out.
Yeah, and examiners know how to break your calculator dependency. They specifically design questions that punish rote memorization.
So our mission for this deep dive is to build your physical intuition so that when you see a formula, you actually understand the logical story it's trying to tell.
Exactly. We are going to strip away the fluff.
We'll start out by laying the groundwork with the bizarre rules of early quantum mechanics. Matter waves and the uncertainty principle.
That's our warm-up. And from there, we'll look at how physical waves actually behave in the real world through optics.
Right, focusing on interference and those really tricky polarization traps. And then we spend the bulk of our time tackling the absolute heavyweight champion of your exam.
The final boss.
Yep, the deep, complex machinery of quantum mechanics the second. We're talking wave functions, normalization calculus, and the dreaded particle in a box.
We will dissect the simple variations and will absolutely tear apart the complex ones.
Because by the time we finish, you won't just survive the exam.
No, you'll be able to reconstruct the underlying physics on the fly, even if you completely blank on a specific variable.
Okay, so let's set the stage. To understand the advanced quantum equations that are going to dominate your final grade, we first have to understand why classical physics failed so spectacularly.
Right, the physics of Isaac Newton and James Clerk Maxwell.
Yeah, because classical mechanics is this beautiful, intuitive system. It works perfectly for predicting the trajectory of a baseball, or like the orbit of Jupiter. So why did physicists at the turn of the 20th century suddenly throw their hands up and say, well, the universe is operating under totally different rules?
Well, the breakdown happened because classical physics was built on a set of assumptions. Assumptions that seemed like common sense, but turned out to be complete illusions of our macroscopic world.
What kind of assumptions?
Well, first, classical physics assumed that energy was continuous. Think of it like a smooth ramp. You can stand at any possible height on that ramp.
Right, no gaps.
Exactly. It also assumed that you could simultaneously measure the exact position and the exact momentum of any object in the universe, provided your instruments were precise enough.
And it also assumed a really strict segregation of phenomena, right? Like a wave is a wave, like a ripple on a pond. And a particle is a particle, like a grain of sand.
Yeah, exactly. The two do not mix.
But as experimentalists began peering into the atomic realm, those assumptions triggered some massive theoretical catastrophes.
Oh, absolutely. The most famous was the ultraviolet catastrophe involving black body radiation.
Right, where classical thermodynamics predicted that an idealized hot object, like, say, an oven, should emit radiation continuously across all frequencies.
Yeah, and the math dictated that as the wavelength of the emitted light got shorter and shorter, moving into the ultraviolet spectrum, the energy should just skyrocket toward infinity.
Which is logically absurd. I mean, if classical physics were true, simply opening a warm oven in your kitchen would release an infinite burst of ultraviolet radiation and X-rays?
Yeah, you'd vaporize the entire neighborhood.
Right. But reality just showed a nice, predictable bell curve of heat and light. Classical physics had absolutely no mechanism to explain why the energy dropped off at higher frequencies.
And then came the photoelectric effect.
Oh, this one is huge for exams.
It really is. So if you shine a light on a piece of metal, Classical wave theory suggested that the light wave should continuously deliver energy to the electrons in the metal.
Like pushing a car to get it rolling.
Exactly. So if
Yeah.
you use a very bright, intense red light, eventually the energy should build up enough to knock an electron loose.
But experiments showed the exact opposite, didn't they?
Yeah, they did. You could blast that metal with a blindingly intense red spotlight for a century, and not a single electron would move.
Wow.
But the moment you turned on a very dim, incredibly weak blue light, electrons were ejected instantly.
And classical physics just couldn't process that, because it proved that the intensity or the amplitude of the wave wasn't what mattered. The only thing that mattered was the frequency.
Right. And the fix for this broken system came from Max Planck and Albert Einstein. They essentially realized that the universe doesn't use smooth ramps.
It uses staircases.
That is the birth of quantization. Planck proposed that energy is exchanged in discrete, indivisible packets called quanta.
And then Einstein took it a step further to explain that photoelectric effect, right?
Exactly. He stated that light itself isn't a continuous wave, but a stream of individual particles, photons.
And each photon carries a specific packet of energy determined strictly by its frequency.
Yeah, so a single blue photon has enough energy to knock an electron loose. But a billion red photons do not, and they can't pool their energy together.
They just bounce off. So that conceptual leap completely shatters the classical segregation of waves and particles. Light acts like a wave when it travels through space, but it acts like a particle when it interacts with matter.
Which brings us to the first massive conceptual hurdle you will face on your exam: de Broglie's matter waves.
Right. Louis de Broglie looked at this wave-particle duality of light and made an incredibly audacious leap of logic.
He argued for a fundamental symmetry in nature. He said, if light, which everyone knew was a wave, can behave like a particle, then perhaps matter, like electrons, protons, atoms, which everyone knew were particles, can behave like waves.
It's an elegant thought. But what does it actually mean for a piece of solid matter to have a wave? I mean, it's not an electromagnetic wave. It's not a physical vibration in a medium like sound.
No, it is a probability wave. It's just a mathematical description of the likelihood of finding that particle in a specific location.
Okay.
And de Broglie derived a relationship connecting the momentum of a physical particle to the wavelength of its guiding probability wave.
And this relationship is the absolute bedrock formula you need to know. Lambda equals Planck's constant divided by momentum. Or, we break it down into its variables, wavelength equals Planck's constant divided by mass times velocity.
Let's look at the structure of this equation, because examiners will test your conceptual understanding of it before they ever make you calculate anything.
Oh, for sure.
The wavelength is inversely proportional to the momentum. So as an object gets more massive or moves faster, its wavelength shrinks dramatically.
Let's visualize this scale. Because if we take a standard macroscopic object, say a golf ball rolling across a green, and plug it into de Broglie's formula, you have a mass of about 46 grams moving at a few meters per second.
And Planck's constant is unfathomably small. It's on the order of 10 to the negative 34.
Right. So when you divide that microscopic constant by the macroscopic momentum of the golf ball, you get a wavelength of roughly 10 to the negative 34 meters.
Which, to put that in perspective, is billions of times smaller than a single proton.
It is so dimensionally insignificant that the wave nature of the golf ball has absolutely zero effect on how it moves. And this is exactly why we don't see quantum weirdness in our daily lives.
Yeah, you won't spontaneously diffract through a doorway when you walk into a room, because your wavelength is practically zero compared to the size of the door.
But of course, the exam won't ask you about golf balls, except maybe as a conceptual trick question. They are going to ask you about electrons.
Right, and an electron's mass is on the order of 10 to the negative 31 kilograms.
Tiny.
Very tiny. So when you run that tiny mass through the denominator of de Broglie's formula, the resulting wavelength jumps up to the scale of nanometers or angstroms.
Which happens to be the exact spacing between atoms in a crystal lattice. So an electron will absolutely diffract, scatter, and interfere with itself when moving through atomic structures.
Now, examiners rarely give you the velocity of an electron directly. That's way too easy.
Right. They want to force you to combine classical kinetic mechanics with quantum formulas.
Exactly. A very common trap involves giving you the kinetic energy of the particle instead of its velocity.
Uh-oh.
Yeah, you have to algebraically manipulate the classical kinetic energy equation. Energy equals 1/2 mass times velocity squared. You manipulate that to isolate momentum.
Okay, so when you do that substitution, de Broglie's formula transforms. Wavelength becomes Planck's constant divided by the square root of 2 times the mass times the kinetic energy. And this is exactly where the trap is sprung.
The unit trap.
Yes.
In atomic physics, nobody measures the energy of a single electron in joules. The joule is a macroscopic unit. It's just far too massive. Instead, they give you the energy in electron volts, or EV.
Right. And 1 electron volt is the amount of kinetic energy an electron gains when it accelerates through a potential difference of 1 volt.
So if an exam question tells you an electron has 150 eV of kinetic energy, and you plug the number 150 directly into that square root denominator, your final answer will be catastrophically wrong.
Like off by orders of magnitude.
Exactly. The formula requires standard SI units to balance correctly with Planck's constant. You must convert the electron volts into joules before you do anything else.
And the conversion factor is the fundamental charge of an electron.
Right.
1.6 times 10 to the negative 19.
Correct. You multiply your EV value by that tiny charge to get your kinetic energy in joules. And only then can you execute the de Broglie calculation.
But let me offer a tactical shortcut for the exam here, because grinding through square roots involving massive scientific notation exponents is just a recipe for a calculator error under time pressure.
Oh, absolutely.
Very often, the question won't even give you kinetic energy. They will just give you the accelerating voltage. They'll say something like, an electron is accelerated through a 10,000 volt potential.
And if you see this specific scenario, an electron and an accelerating voltage, you can bypass the entire mathematical headache.
Yes, there is a derived shortcut formula that pre-calculates all the constants. The mass of the electron, Planck's constant, the charge of the electron.
The shortcut is wavelength equals 12.27 divided by the square root of the voltage.
And the critical thing to remember is that this shortcut spits the answer out directly in angstroms, not meters.
It is an incredible time saver. Think about it. If your accelerating voltage is 10,000 volts, the square root is simply 100.
So you just divide 12.27 by 100.
Exactly. And you instantly know the wavelength is 0.1227 angstroms. You've solved a 5-minute calculation in 10 seconds.
Leaving you way more time for the harder sections. Okay, so we have established that matter behaves as a wave. The direct consequence of this wave nature brings us to probably the most philosophically unsettling concept in the warm-up section of your syllabus, Heisenberg's uncertainty principle.
Students often misunderstand this principle as an engineering problem. They assume that if we just build a better microscope or, use more sensitive lasers, we could measure a particle's exact location and exact speed simultaneously.
But it has nothing to do with the quality of our instruments, does it?
No, not at all. It is a fundamental property of the universe, directly tied to what it means to be a wave.
Think about a pure, perfect sine wave moving across a graph. It has a single, perfectly defined wavelength. And because momentum is completely dependent on wavelength, this pure wave has a perfectly defined momentum.
But where is that wave located?
Exactly. A perfect sine wave extends infinitely in both directions. It has no single position.
Right. To create a localized wave, a wave packet that is confined to a small region of space, giving the particle a somewhat defined position, you have to mathematically add together hundreds or thousands of different sine waves, all with slightly different wavelengths.
And as soon as you add different wavelengths together to pinch the wave into a specific location, you no longer have a single wavelength. You no longer have a single momentum.
You've sacrificed the certainty of momentum to gain the certainty of position.
The more you squeeze the spatial position, the more the momentum spectrum bulges out. And Heisenberg formalized this trade-off into an inequality.
The uncertainty in position, multiplied by the uncertainty in momentum, must be greater than or equal to Planck's constant divided by 4 pi.
On the exam, you will almost exclusively deal with the minimum boundary of this inequality, basically treating it as an equation equal to Planck's constant over 4 pi. And remember, since mass generally doesn't change, the uncertainty in momentum is simply the mass multiplied by the uncertainty in velocity.
But examiners love to test your attention to detail here with what I call the percentage accuracy trap.
Oh, this one is brutal.
It is. A standard question reads, an electron is traveling at 500 meters per second, and this velocity is known to an accuracy of 0.01%. Calculate the minimum uncertainty in its position.
The trap is glaringly obvious, but under exam pressure, it's devastating. Students see the velocity, 500, and they just plug that number directly in as the uncertainty in velocity.
Which is completely illogical. The velocity isn't the uncertainty. The uncertainty is the margin of error.
Right.
You have to take that percentage, convert it to a decimal, and multiply it by the velocity. So 0.01% is 0.0001. Multiply that by 500, and your actual uncertainty and velocity is 0.05 meters per second.
And that is the number you plug into the Heisenberg formula.
Exactly. It's all about reading comprehension.
But my favorite application of Heisenberg, and honestly a guaranteed high point value question on a tough exam, is using this principle of uncertainty to prove a massive structural fact about the atom. We call it the confined space problem.
Ah, this is a beautiful piece of physics.
Yeah. The question simply asks you to prove mathematically whether or not an electron can physically exist inside an atomic nucleus.
Right, because we are using a simple inequality to deduce the architecture of the universe. To solve it, you have to assume the premise is true to see if it breaks the laws of physics. Let's assume an electron is trapped inside the nucleus.
Okay, so if it's trapped in the nucleus, then the absolute maximum uncertainty in its position is the physical diameter of the nucleus itself. It has to be in there somewhere. Let's say the diameter of a typical nucleus is roughly 10 to the negative 14 meters.
We use that tiny distance as our uncertainty in position. We plug that into Heisenberg's equation to find the corresponding uncertainty in momentum.
And when you divide Planck's constant by the product of 4 pi and that tiny position uncertainty, you get a tremendously large momentum uncertainty.
And here is where the physics clicks into place. If the electron has that massive amount of momentum uncertainty, it must possess, at a minimum, an equivalent amount of kinetic energy.
Right, so we convert that momentum into kinetic energy using the classical formula. Kinetic energy equals momentum squared divided by twice the mass.
When you grind through the math, square the massive momentum, divide by the tiny mass of the electron, and convert the resulting joules into mega electron volts, the kinetic energy required for an electron to be confined to a space that small comes out to roughly 40 to 50 mega electron volts.
Depending on the exact nuclear radius you use, sometimes it's much higher.
Exactly, and this is the punchline. The strong nuclear force, the binding energy that holds a nucleus together, operates on the scale of about 8 mega electron volts.
So if an electron were forced into a space as small as the nucleus, its inherent quantum momentum would generate so much kinetic energy that it would violently overpower the binding energy of the atom.
It would explode outward. The mathematics explicitly forbid the electron from residing in the nucleus.
It must exist in an orbital shell far away, where the allowed volume is large enough that its momentum uncertainty drops to a manageable level. You use an abstract mathematical trade-off to prove why matter is stable. It's just stunning.
It really is. And that wraps our warm-up. We've established the wave nature of matter.
But before we dive into the deep end of solving the heavy quantum wave equations in our final section, we need to transition to the middle tier of your syllabus, optics.
Now, you might be asking, why are we talking about light waves in the middle of a quantum mechanics deep dive?
Yeah, it seems out of place.
But it's not, because the mathematical and physical rules of wave interference that you learn in optics are the exact same mechanisms that govern the probability waves in advanced quantum mechanics.
Right. If you don't understand how light interferes, you cannot understand how an electron trapped in a box behaves.
The foundational concept in optics is superposition. When two waves occupy the same space at the same time, they don't crash into each other like billiard balls.
No, they pass through each other. And while they are overlapping, their actual displacements add together algebraically.
Imagine standing in a massive sports stadium. If the crowd on one side of the stadium stomps their feet in perfect rhythm with the crowd on the other side, the sound waves meet in the middle, peak to peak, and amplify each other. The sound becomes deafening.
That is constructive interference. But if one side stomps exactly half a beat out of sync with the other, the peak of one sound wave meets the trough of the other. The pressures cancel out.
That is destructive interference. It's the exact principle behind noise-canceling headphones. A microphone picks up ambient sound, and the headphone speaker generates an identical sound wave perfectly out of phase to cancel it out.
For light waves, constructive interference creates a bright fringe, and destructive interference creates a dark fringe. The mathematics of this rely entirely on the path difference between the two waves.
Right. If one wave travels exactly one full wavelength further than the other, they still match up perfectly peak to peak. Constructive.
But if one travels an extra half wavelength, they are totally out of sync. Destructive.
And this simple geometric rule becomes incredibly treacherous when applied to thin film interference.
Oh boy.
Yeah. Think of a soap bubble shimmering with colors or a slick of oil on a wet road. A thin film has a top surface and a bottom surface. Light hits the top surface, and some of it reflects back. The rest of the light penetrates the film, hits the bottom surface, and reflects back up.
So you now have two reflected light waves that are traveling back to your eye. The wave that went down to the bottom surface traveled a longer distance.
And that extra geometric path difference is calculated as 2 times the refractive index of the film, multiplied by the thickness of the film, multiplied by the cosine of the angle of refraction.
If the exam question stopped there, it would be a simple geometry problem. But this is where the most notorious trap in the optics section waits for you. Stokes' law.
Stokes' law describes a phenomenon that alters the phase of a wave upon reflection, totally independent of how far it traveled.
We need to explain the physical mechanism behind Stokes' law, because if you understand why it happens, you will never fall for the trap.
Okay, imagine you have a lightweight jump rope tied securely to a massive, immovable brick wall. You whip the rope to send a wave pulse traveling toward the wall.
When the wave hits the heavy, unyielding wall, the wall pushes back against the force. This reaction force causes the wave to snap back upside down. A crest hits the wall, and it reflects back as a trough. The wave has been inverted.
Mathematically, flipping a wave upside down is a 180-degree phase shift. And a 180-degree phase shift is physically identical to shifting the wave forward by exactly half a wavelength.
Right. Now imagine the opposite scenario. The jump rope is not tied to a wall. It is tied to a loose metal ring that can slide freely up and down a pole.
When the wave pulse reaches the pole, the ring slides upward with the energy of the wave and then snaps back down, sending the wave back exactly as it came. A crest reflects as a crest. There is no inversion, no phase shift.
So in optics, the brick wall is an optically denser medium. A material with a higher refractive index, meaning light travels slower through it. The loose pole is a rarer medium.
So Stokes' law dictates that when light reflects off a boundary where the material on the other side is denser, the wave inverts. It suffers an artificial half-wavelength phase shift.
But if it reflects off a boundary where the material is rarer, nothing happens.
Let's apply this to a standard exam scenario. So scenario a soap film floating in the air. The refractive index of air is basically 1. The index of soap is around 1.3.
Okay, so the first wave hits the top surface of the soap. It's traveling from air, hitting soap, rare hitting dense. It hits a brick wall.
Yep, so that first reflected wave suffers a half-wavelength phase shift. It flips.
The light that passed through the film now reaches the bottom surface. It is traveling inside the soap, and it hits the boundary with the air outside. Dense hitting rare, the loose pole.
Right, it reflects normally with no phase shift.
So when these two reflected waves finally meet up to interfere, one of them has been artificially flipped upside down and the other hasn't. This completely scrambles the standard rules of interference.
Exactly. Because one wave is naturally out of sync by a half wavelength, the traditional geometric condition for a bright fringe, that the path difference must equal a whole number of wavelengths. Well, now that produces a dark fringe.
The conditions completely swap.
Yes. For a film suspended in air, the condition for constructive interference, a bright fringe, requires the geometric path to equal an odd multiple of a half wavelength.
And examiners know you will memorize these swapped conditions, so they will test you with scenario B, an oil slick on a puddle of water, or a thin film of water sitting on a piece of glass.
Let's trace the physics. Water has an index of 1.3, glass is 1.5.
The light hits the top surface. Air to water, rare to dense. The first wave reflects and gets an artificial half-wavelength shift. It flips upside down.
The rest of the light travels through the water and hits the bottom boundary with the glass. Water to glass, 1.3 to 1.5. It is hitting a denser medium again.
Another brick wall.
So the second reflected wave also suffers a half-wavelength phase shift. It also flips upside down.
Wait, if both waves are flipped upside down, they remain in perfect sync with each other. The two phase shifts mathematically cancel each other out completely.
Which means the interference conditions swap back to standard geometry. In a film resting on a denser medium, a whole wavelength path difference creates a bright fringe, and a half-wavelength difference creates a dark fringe.
So the golden rule for surviving thin film questions is simply this. Count the denser reflections. If there is an odd number of denser reflections, usually just the top surface, you must use the swapped phase conditions.
And if there is an even number of denser reflections, the shifts cancel and you use standard conditions. Count your phase shifts.
This same Stokes' law mechanism is the beating heart of the next major optical setup you will face, Newton's rings. This is a brilliant 17th century experiment that produces perfect concentric circles of light and dark fringes.
The physical setup is crucial here. You take a perfectly flat plate of glass, and you place a plano-convex lens on top of it, with the curved side resting on the plate.
It touches the plate at a single point in the dead center.
Because the lens curves upward, away from the flat plate, it creates a microscopic wedge of air trapped between the two pieces of glass. This air gap is a thin film whose thickness increases perfectly symmetrically as you move away from the center.
And because the thickness is perfectly symmetrical in a circle around the center point, the interference fringes form perfect circular rings. Now, examiners love to ask a qualitative question before the math. Is the exact center spot of Newton's rings bright or dark? And why?
Well, at the exact center, the lens is physically touching the glass plate. The thickness of the air film is 0. Geometrically, there is 0 path difference between the wave reflecting off the top of the air gap and the wave reflecting off the bottom.
If you rely purely on geometry, 0 path difference should mean perfect constructive interference. It should be a bright spot.
But if you look at the rings in a lab, the center spot is pitch black.
Why? Because of our jump rope analogy.
Yeah.
Look at the two reflections. The first reflection is light moving down through the glass lens, hitting the air gap. Glass to air, dense to rare, no phase shift.
And the second reflection is light traveling through that impossibly thin air gap, hitting the flat glass plate at the bottom, air to glass, rare to dense, the brick wall.
That second reflection suffers an automatic 180-degree phase shift. Because the physical distance between the lenses at the center is 0, that single artificial phase shift is the only difference between the two waves.
One wave is flipped perfectly upside down relative to the other. Peak meets trough. Perfect. Total destructive interference.
The formula for Newton's rings allows you to find the diameter of any given dark ring based on the wavelength of light and the curvature of the lens. The diameter of the nth dark ring squared equals 4 times the ring number times the wavelength times the radius of curvature of the lens.
It's a beautiful, clean formula. But this brings us to the complex exam problem, the dust particle trick.
Oh, this one is sneaky.
You will almost never see an exam question that gives you the diameter of just one ring and asks you to solve for the wavelength.
Instead, they will give you the diameters of 2 different rings. They will say the 5th dark ring had a diameter of 3 millimeters, and the 15th dark ring has a diameter of 6 millimeters.
Why do they complicate it? Why not just use the 5th ring and be done with it?
Because physics exams are designed to simulate real-world laboratory conditions. In a real 19th century optics lab, it was physically impossible to create an environment perfectly free of contaminants.
Exactly. When you place a heavy glass lens on a flat glass plate, 9 times out of 10, a microscopic speck of dust will be trapped between them.
And that single speck of dust completely ruins the geometry. The lens isn't actually touching the glass plate at the center anymore. It is propped up slightly.
The central thickness isn't 0. It is some unknown, unmeasurable extra thickness.
Because the entire lens is propped up, that unknown extra thickness is added to the air gap at every single point. It shifts the diameter of every single ring outward by an unpredictable amount.
If you just take the diameter of the 5th ring and plug it into the basic formula, your calculated wavelength will be completely wrong because the basic formula assumes perfect contact.
So how on earth do you solve the problem if you have an unknown, unmeasurable error contaminated the entire system?
You use algebra to make the error destroy itself. If you write out the equation for the nth ring, including the unknown error term, and then you write out the equation for the mth ring, including the exact same unknown error term.
Because it's the exact same dust particle propping up the whole lens.
Precisely. You have a system of 2 equations with the same constant error. If you subtract the equation of the smaller ring from the equation of the larger ring, the unknown error term completely cancels out. It vanishes from the math.
The resulting subtraction formula is your exam lifesaver. The diameter of the larger ring squared minus the diameter of the smaller ring squared equals 4 times the difference in their ring numbers, multiplied by the wavelength, multiplied by the radius of curvature.
By analyzing the difference between 2 rings, rather than the absolute size of one ring, the experimental imperfection is completely bypassed. If an exam question gives you 2 rings, immediately write down the subtraction formula. Do not attempt to calculate them individually.
That is the elegance of experimental physics built into a mathematical trick. All right, we have one final optics hurdle before we reach the quantum heavyweight section: polarization.
This concept shifts our focus from the longitudinal spacing of a wave to its transverse orientation.
Imagine a light wave not as a simple ripple, but as an oscillating electric field. Light emitted from an incandescent bulb is unpolarized. The electric fields of the countless photons are oscillating randomly in every possible direction perpendicular to the direction the light is traveling.
Up, down, left, right, and every diagonal angle in between.
A polarizer is an optical filter that acts like a microscopic picket fence. It only allows electric fields that are oscillating parallel to the gaps in the fence to pass through. All the other random oscillations are blocked or absorbed.
What emerges on the other side is perfectly polarized light, oscillating in one single defined plane.
There are two crucial laws of polarization you will be tested on. First is Brewster's law, which explores how you can polarize light without a filter just by bouncing it off a surface.
If you shine unpolarized light at a surface like a lake or a glass window at various angles, the reflected light will be partially polarized. But at one very specific angle of incidence, the reflected light becomes 100% perfectly polarized horizontally.
This is the angle that polarized sunglasses are designed to block, which is why they eliminate the glare off a highway. The formula to find this specific angle, the polarizing angle, or Brewster's angle, is beautifully simple.
The tangent of the polarizing angle equals the refractive index of the material.
You need to know the physical mechanism driving Brewster's law because examiners love to test the geometry of it. When unpolarized light hits the glass, it forces the electrons in the glass to vibrate.
These vibrating electrons act as tiny antennas, re-radiating the light back into the air as the reflected ray.
But an antenna cannot radiate energy along the axis of its own vibration. If an electron is bouncing strictly up and down, it radiates outward horizontally, but it shoots zero energy straight up or straight down.
Exactly. At Brewster's specific angle, the geometry aligns perfectly so that the refracted ray traveling into the glass is at an exact 90-degree angle to the reflected ray bouncing off the surface.
Wait, because they are exactly 90 degrees apart, the electrons vibrating in the glass parallel to the reflected ray cannot radiate any energy in the direction of the reflection.
Right. That specific plane of oscillation is physically silenced. So the reflected ray is entirely stripped of that polarization component, leaving it perfectly polarized in the remaining plane.
A standard multiple-choice question will describe Brewster's angle and ask for the angle between the reflected and refracted rays. The answer is always exactly 90 degrees.
The second law of polarization is Malice's law. This law dictates what happens when you take light that is already polarized and you force it through a second picket fence, which we call an analyzer.
If the slits in the second fence are perfectly parallel to the first, 100% of the polarized light passes through. But if you rotate the second fence by 90 degrees, so they are crossed, the light is completely blocked.
A vertical wave cannot pass through horizontal slits. The intensity drops to absolute zero.
Malice's law mathematically describes the intensity of light at any rotation angle in between. The final intensity equals the initial intensity multiplied by the cosine squared of the angle between the two polarizers.
Which brings us to the ultimate mind-bending polarization exam trap, the three Polaroids problem. Listen closely because your intuition will scream at you to choose the wrong answer.
Here is the setup. You have an initial beam of unpolarized light with an intensity we will call I0. It hits a vertical polarizer.
Rule 1. Whenever unpolarized light passes through a polarizer, exactly half of the light is blocked and half gets through. The new intensity is I0 divided by 2. It is now vertically polarized.
Next, that vertically polarized light hits a second polarizer, the analyzer, that is crossed horizontally at a 90-degree angle to the first.
According to Malice's law, the cosine of 90 degrees is 0. 0 squared is 0. All the light is blocked. The intensity on the other side of the second filter is pure darkness.
Now for the trick. You take a third polarizer and you slide it right into the middle, between the crossed vertical and horizontal filters, and you orient this middle filter at a 45-degree angle. What happens to the final intensity?
Your classical intuition will tell you that adding an obstacle to a system that is already blocking 100% of the light can only make things darker.
Right. If two brick walls block a hallway, building a third wall between them shouldn't suddenly open a door. Most students will confidently write that the final intensity remains 0.
But quantum optics does not care about your intuition. You have to trust the math and follow the light wave step by step. We know the light leaves the first vertical polarizer with an intensity of I0 over 2. It is vibrating strictly vertically.
Now it hits the middle polarizer, which is rotated 45 degrees. The vertical electric field cannot pass through untouched, but it isn't completely blocked either.
The field vector essentially projects a shadow of itself onto the 45-degree axis of the middle filter. We use Malice's law to find the intensity of that shadow.
The new intensity is the incoming intensity, I0 over 2, multiplied by the cosine squared of 45 degrees. The cosine of 45 is 1 over the square root of 2. When you square that, it becomes exactly 1/2.
So we multiply I0 over 2 by 1/2. The intensity that successfully passes through the middle filter is I0 divided by 4. Light got through.
But here's the critical part, the physical shift that makes the magic happen. When that light passed through the middle filter, the filter physically forced the light wave to rotate.
The light is no longer vibrating vertically, it is now vibrating diagonally at a 45-degree angle.
Now, this diagonally polarized light approaches the final horizontal polarizer. Yes, the final polarizer is 90 degrees relative to the first one, but the light has forgotten the first polarizer.
Relative to the light's current diagonal orientation, the final horizontal polarizer is only 45 degrees away.
We apply Melisse's law one last time. The incoming intensity is I0 over 4. The relative angle is 45 degrees. The cosine squared of 45 is another 1/2.
We multiply I0 over 4 by 1/2. The final intensity emerging from the system is I0 divided by 8.
By placing a physical obstacle directly into the path of absolute darkness, you force the light wave to mathematically twist its orientation, allowing a fraction of it to sleuth through the final gate.
The intensity goes from 0 up to 1/8. It is a brilliant puzzle, and it requires you to analyze each interaction in isolation. Do not jump to the end. Follow the light.
Take a breath. We have cleared the optics mid-tier. We understand wave interference. We understand phase shifts. We understand boundary mechanics. It is time to enter the deepest waters of the exam.
We are transitioning to the final boss, quantum mechanics II. This is where everything you've learned so far merges into a unified, mathematically rigorous description of reality.
In Section 1, we learned that an electron is a probability wave. In Section 2, we learned how waves interfere and reflect at boundaries. Now we have to build the actual equations that govern those quantum waves.
The foundational element of modern quantum mechanics is the wave function, universally represented by the Greek letter Sais.
Every physical property of a quantum particle, its energy, its momentum, its location, is perfectly encoded within this single mathematical entity.
But we need to be incredibly clear about what psi actually is, and more importantly, what it is not. If you drop a pebble in a pond, you can physically see the water wave propagating outward. You can measure the height of the water.
Psi is not a physical wave propagating through space.
No, psi is a purely abstract mathematical function. To make matters worse, it is a complex function. It contains an imaginary component, the square root of -1.
Because our physical universe does not have imaginary dimensions, the wave function, psi, on its own, has absolutely no physical meaning. You cannot build a detector to measure psi.
I find it helpful to think of psi as the architectural blueprint for a building. The blueprint contains every single detail of the building structure, where the walls are, where the plumbing runs.
But you cannot sleep inside a blueprint. It isn't a physical structure. To get the physical reality, you have to execute an operation based on the blueprint.
That operation was discovered by physicist Max Born, who provided the crucial interpretation that makes quantum mechanics usable. Born realized that while psi itself is an imaginary ghost, if you take the absolute value of psi and square it,
Represented mathematically as the modulus of psi squared.
right, the imaginary numbers cancel out, leaving you with a purely real, positive number.
And what does that real number represent? It is the probability density. It tells you the exact mathematical probability of finding the particle in a specific, tiny volume of space at a specific moment in time.
If you map the square of psi across a region, the areas where the value is highest are the areas where the electron is most likely to be found.
But for a mathematical blueprint to describe a real physical particle, it must obey a strict set of logical constraints. An examiner will frequently ask you to evaluate whether a random mathematical function is a valid wave function.
A valid wave function must be single-valued. You can't have a blueprint that says a wall has a 20% chance of being here and an 80% chance of being in the exact same spot at the exact same time.
It must be continuous. Nature does not tolerate jagged, instantaneous teleportation breaks in a wave. And most crucially, it must be normalized.
Normalization is a mathematical guarantee of existence. If an electron exists, it has to be somewhere in the universe.
If you calculate the probability of finding the electron in one tiny box, it might be 1301%. If you calculate the probability for every single tiny box across the entire infinite expanse of the universe, and you add all those probabilities together, the total sum must equal exactly 1, or 100%.
It is a certainty that the particle is somewhere. To find the wave function that obeys these rules, we use the engine of quantum mechanics. the Schrödinger equation.
Yeah. The full time-dependent Schrödinger equation tracks how a wave function evolves over time. But for the majority of standard quantum mechanics exams, you will be wrestling with the time-independent Schrödinger equation, the TICE.
The TICE is used to find the stationary states of a system, the stable, unchanging standing waves that an electron forms when it is bound in an atom or a confined space.
When you look at the equation, it is a terrifying string of partial derivatives, reduced Planck's constants, and complex variables.
Let's read the core structure of the TICE out loud and then translate it back into plain English.
Okay, here we go. The second derivative of psi with respect to space, plus the quantity 2 times the mass, divided by Planck's constant barred squared, multiplied by the quantity total energy E minus potential energy V, multiplied by psi equals 0.
Let's strip away the terrifying calculus terminology. The expression E minus V is simply total energy minus potential energy. In classical physics, total energy minus potential energy leaves you with kinetic energy.
The second derivative of a wave function simply describes how sharply the wave is curving at a given point. And a wave that curves very sharply has a very short wavelength, which, as we learned from de Broglie, means it has a very high momentum and therefore high kinetic energy.
So when you look past the intimidating notation, the time-independent Schrödinger equation is just a fundamental statement of the conservation of energy. It is an accounting ledger.
It balances the kinetic curvature of the wave with the potential energy of the environment to guarantee that the total energy remains constant.
Understanding that structure allows you to manipulate it. And the first manipulation you will be tested on is Formula Dive 6, normalization calculus.
You will be handed a completely arbitrary wave function and asked a simple question. Is this function normalized?
To prove it, you have to execute the math behind the concept we discussed earlier. You have to add up all the probabilities across the entire allowed space. In calculus, adding up an infinite number of continuous values is called integration.
You set up an integral. You integrate the absolute square of the wave function, probability density, over the boundaries of the system.
If the particle is trapped in a box of length L, your integration limits are 0 to L. If the integral evaluates to exactly the number 1, then the function is already perfectly normalized. You're done.
However, the function they give you will almost never evaluate to 1. The integral will spit out some arbitrary algebraic mess like L divided by 2.
This means the total probability of the particle existing is somehow L over 2, which makes absolutely no physical sense.
So you have to fix the blueprint. You have to find a normalization constant, usually denoted by a capital A, that scales the entire wave function up or down so that the final area equals 1.
The algebraic trick to finding A is beautifully straightforward. Once you evaluate the integral of the unnormalized function, your normalization constant A is simply equal to 1 divided by the square root of whatever your integral evaluated to.
If your integral evaluated to L over 2, you flip it and take the square root. Your constant A is the square root of 2 over L.
You slap that constant onto the front of the original wave function, and you have successfully normalized it.
But there is a massive calculus trap hiding in this process. To execute this integration, you have to square the wave function. Since most quantum boundaries are analogous to vibrating strings, the wave functions you are given will almost entirely be sine or cosine functions.
So you will find yourself staring at an integral of a sine squared function. If you try to integrate sine squared directly using standard power rules, you will hit a brick wall. You will waste 20 minutes on the exam spinning your wheels.
You must utilize a trigonometric identity to flatten the square into a linear function that can be easily integrated. The critical identity to memorize is sine squared of theta equals 1 minus the cosine of 2 theta, all divided by 2.
If you replace the sine squared term with that identity, the calculus shatters into 2 incredibly easy pieces. The integral of a constant is just x, and the integral of cosine is sine.
A terrifying 20-minute calculus nightmare becomes a 3-line, foolproof derivation. Memorize that identity.
That identity is your primary weapon for surviving the ultimate undisputed final boss of the entire physics syllabus. Formula Dive 7, the particle in an infinite potential well, also universally known as the rigid box.
This is the proving ground. Every concept we've discussed, matter waves, quantization, boundary conditions, probability integrals, they all collide in this single problem.
The setup is deceptively simple. Imagine an electron trapped on a one-dimensional line of length L.
At the edges of this line, at position 0 and position L, there are walls. But these are not physical walls made of bricks. They are walls of infinite potential energy.
Meaning that for an electron to exist outside the box, or even exactly on the edge of the box, it would require an infinite amount of energy, which is physically impossible.
Therefore, the probability of finding the electron at the walls or beyond them is absolute zero. This defines our rigid boundary conditions.
Whatever mathematical shape the wave function takes inside the box, the value of psi must drop to exactly 0 at the boundaries. Psi at 0 equals 0. Psi at L equals 0.
This creates a physical scenario identical to plucking a guitar string that is clamped down at the nut and the bridge. The string can vibrate in a single large arch, can vibrate in an F shape with a stationary node in the exact middle.
But it cannot vibrate in a shape where the clamped ends are moving.
Because the wave function is clamped at 0 at the boundaries, only certain specific, perfect sine waves can physically fit inside the box without breaking the boundary conditions.
You can fit half a wave, a full wave, 1.5 waves. But you cannot fit 1.13 waves, because the end of the wave wouldn't hit 0 at the wall.
This geometric restriction is the origin of quantization, because only specific wavelengths are allowed to exist in the box, and we know from de Broglie that wavelength dictates momentum, and momentum dictates kinetic energy.
The electron is only allowed to possess certain specific discrete energy levels. It cannot possess an energy that falls between those levels because that would correspond to a wave that doesn't fit the box.
When you plug these sine wave boundary conditions into the Schrödinger equation, you derive the single most important equation on your test. The energy of the nth quantum state, E sub n, equals n squared multiplied by Planck's constant squared, all divided by 8 times the mass times the length of the box squared.
This formula reveals a profoundly unsettling fact about the quantum universe. Look at the quantum number n. It dictates the energy level, 1, 2, 3, and so on. What happens if n equals 0?
If you plug 0 in for n, the energy is 0. If the energy is 0, the momentum is 0. The wavelength becomes infinite, the wave function goes flat, and the probability of finding the particle drops to 0 everywhere.
The particle ceases to exist.
Furthermore, an energy of exactly 0 violates the Heisenberg uncertainty principle. If the particle is trapped in a box of length L, its position is somewhat constrained.
Therefore, its uncertainty and momentum cannot be 0. It must possess some inherent irreducible kinetic energy just by existing in a confined space.
The universe literally forbids absolute stillness. The lowest possible state the particle can exist in is when n equals 1. This is called the zero-point energy, or more commonly on exams, the ground state energy.
Calculating the ground state energy is the most basic exam problem for the rigid box, but it is a graveyard for students who are sloppy with their units.
The examiner will ask, calculate the ground state energy of an electron trapped in a rigid one-dimensional box of length 1 angstrom. It sounds like a plug and chug. You set n to 1. But the unit traps are waiting.
The length of the box L is given in angstroms. You must convert it to meters. 1 angstrom is 10 to the negative 10 meters.
The formula requires you to square the length in the denominator, which drops it to 10 to the negative 20. You must use the mass of an electron in kilograms, 9.1 times 10 to the negative 31. You must square Planck's constant in the numerator.
You are juggling exponents ranging from negative 68 to negative 51. You have to practice inputting these massive scientific notations into your specific calculator model before exam day.
If you don't use parentheses correctly, your calculator will divide when it should multiply, and your answer will be off by 40 orders of magnitude.
When you execute the math correctly, the energy will come out in joules. But physics professors rarely want the final answer in joules. They want it in electron volts.
So you must divide your final joule answer by 1.6 times 10 to the negative 19. For a standard 1 angstrom box, the ground state energy sits right around 37.7 electron volts.
Once you have the ground state energy, the exam will escalate to type 2 problems, energy transitions. An electron absorbs a photon and jumps to a higher energy level. They will ask you to calculate the energy required to make the jump.
The formula for a transition is beautifully simple because the energy levels scale with the square of the quantum number. The energy at level n is just n squared times the ground state energy.
The energy difference between two states is simply the square of the final state minus the square of the initial state, multiplied by the ground state energy.
But this is where the terminology trap springs. The trap is so effective because it exploits basic counting logic. The ground state is n equals 1. If an exam asks you for the transition from the ground state to the first excited state, what is the quantum number for the first excited state?
Logically, students hear first, and they plug in n equals 1. But n equals 1 is the ground state. The first state above the ground state, the first excited state, is n equals 2.
And if they ask for the second excited state?
The second excited state is n equals 3. The quantum number n is always one integer higher than the named excited state.
If a question asks for the energy required to jump from the ground state to the second excited state, you are calculating the jump from n equals 1 to n equals 3. The formula is 3 squared minus 1 squared.
9 minus 1 is 8. The jump requires 8 times the ground state energy.
If you fall for the terminology trap and use n equals 2, you calculate 4 minus 1, which is 3 times the ground state energy. You lose all the points.
Read the terminology with absolute paranoia. Now we reach the apex of mathematical difficulty on the exam. Type 3 problems, probability integrals.
The examiner will ask, what is the exact probability of finding the particle between position L over 4 and position 3L over 4?
To solve this, you have to use the normalized wave function for a particle in a box, which is the square root of 2 over L, multiplied by the sine of n times pi times x over L.
You must square that entire function. Set up your integral between the requested limits, employ the half-angle trig identity to break down the sine squared term, and grind through a full page of calculus.
You should know how to execute that calculus. But before you touch your pencil to the paper, you must look for the symmetry shortcut. The wave functions inside the box are highly symmetrical.
If you are looking at the ground state, n equals 1, the wave is a single perfect arch that peaks exactly in the dead center of the box at L over 2. The left half of the box is a perfect mirror image of the right half.
So if the question asks, what is the probability of finding the ground state electron in the left half of the box from 0 to L over 2?
You do zero math. By pure geometric symmetry, exactly half of the probability area is on the left and half is on the right. The answer is 0.5 or 50%. Write it down and move to the next question.
But examiners know about the shortcut, so they will twist the geometry to force you to integrate. They will ask for the probability of finding the particle in the middle 50% of the box, from L over 4 to 3L over 4.
It is incredibly tempting to guess that the answer is 0.5 again, since you are asking about 50% of the physical space of the box.
But the probability density is not flat. The ground state wave bulges massively in the center. The amplitude is highest there, which means the likelihood of finding the particle is highest there.
If you run the brutal page of calculus for the middle 50%, the integrated answer comes out to exactly 1/2 plus 1 over pi, which valuates to roughly 0.818.
Even though the middle section only represents 50% of the physical space, the electron spends 81.8% of its time there.
If you're grinding through the calculus on the exam and your final decimal is close to 0.818, you know with absolute certainty that your integration was flawless. It is a fantastic anchor point to memorize.
Let's close out the theoretical depth of quantum mechanics by bringing the rigid box back to reality. The infinite potential, well, is a mathematical idealization.
In the real physical universe, there are no walls of infinite potential. The walls holding an electron in a metal or the nuclear forces holding a proton are very steep, but they are finite. They have a specific height, a specific potential energy, which we'll call V0.
If a wall has a finite height, the boundary conditions change. The wave function is no longer forced to be exactly 0 at the wall. It can penetrate the wall slightly, decaying exponentially into the classically forbidden region.
This is the mechanism behind quantum tunneling. But I want to look at a different, even weirder scenario that ties our entire deep dive perfectly together.
What happens when the particle approaches a finite potential step, but the particle actually has more kinetic energy than the height of the step? The energy E is greater than V0.
Think about classical physics. You roll a marble toward a ramp. The marble has enough kinetic energy to clear the height of the ramp. What happens?
The marble rolls up the ramp, loses some kinetic energy to potential energy, but it easily clears the top and keeps rolling on the higher plateau. It is a 100% transmission rate. It definitely goes over.
But a quantum particle is not a marble. It is a wave. When the wave hits the potential step and climbs onto the plateau, its kinetic energy drops.
According to de Broglie's bedrock formula from the very beginning of our journey, if kinetic energy drops, momentum drops. And if momentum drops, the wavelength changes. The wave physically stretches out.
The particle is a wave passing from an area of one wavelength to an area of a different wavelength. Where did we see this exact phenomenon before?
In the optics section, when light passes from air into a denser medium like glass, its wavelength changes due to the refractive index.
And what happens at the boundary where the wavelength changes?
You get reflection. Even though the light has plenty of energy to pass through the glass, the abrupt shift in the wave properties forces a percentage of the wave to reflect backward.
The exact same optical mechanics govern the quantum particle. When the electron hits the potential step, even though it possesses more than enough energy to fly right over the wall, The abrupt change in its de Broglie wavelength causes the probability wave to partially reflect off the boundary.
There's a mathematical probability that an electron with enough energy to overcome an obstacle will simply bounce off the empty space above the obstacle and turn around.
It is an effect completely devoid of classical logic. It is pure quantum wave mechanics governed by the exact same reflection formulas we used for light waves hitting a glass plate.
It is mind-bending. The universe doesn't care if it's an ocean wave, a light wave, or a wave of pure probability. The fundamental architecture of interference and boundary reflection is universal.
And if you can understand those universal themes, you won't just be memorizing equations. You will be speaking the language of the exam.
We did it. We survived the final boss. We have navigated the deepest, darkest waters of the physics syllabus.
Let's hit into the outro and summarize the ultimate tactical survival guide for exam day.
If you take nothing else away from this intense session, burn these 3 tactical rules into your memory. Rule 1. The unit trap is the most common cause of failure.
Always convert your variables into standard SI units before applying a quantum formula. Electron volts must become joules, angstroms must become meters, percentages must become decimals.
The calculus might be hard, but it is the arithmetic that will kill your grade.
Rule 2. When dealing with thin film optics and Newton's rings, count your phase shifts to avoid the Stokes law trap. Remember the heavy rope and the loose ring.
Every reflection off an optically denser medium creates an artificial half-wavelength shift. One dense reflection means your interference conditions swap. 2 dense reflections mean they cancel out and you use standard geometry.
And Rule 3. Read the nomenclature of quantum states with extreme suspicion. The ground state is n equals 1. The first excited state is n equals 2.
Never let a basic vocabulary word sabotage a flawless Schrödinger integration.
All right, before we let you go, I want to leave you with one final, deeply provocative thought to mull over while you study. Throughout this entire journey, we have constantly compared the bizarre quantum world to the intuitive classical world.
We proved that a golf ball is classical and an electron is quantum. But there's a concept in physics known as the correspondence principle.
The correspondence principle states that the rules of quantum mechanics must eventually blend seamlessly into the rules of classical mechanics as systems get larger and larger.
As the quantum number n approaches infinity, the discrete quantized energy staircases smooth out and they become the continuous classical energy ramps we experience every day. The fuzzy probabilities of the wave function eventually collapse into solid, predictable certainty.
We saw it when we looked at the scale of de Broglie waves. If you calculate the quantum state of a tiny 1 milligram dust speck moving at a sluggish 3 centimeters per second inside a tiny 1 centimeter box, its quantum number n isn't 1 or 2.
It is roughly 9 times 10 to the 23rd.
At that impossibly high quantum state, the distance between the quantized energy levels is so infinitesimally microscopic that the energy appears completely continuous.
The quantum effects vanish entirely. The dust speck behaves like a perfectly classical object.
But here is the question that keeps physicists awake at night, the question I want you to think about. We know a 1 milligram dust speck is classical. We know an electron is quantum. But what about the space in between?
What about a massive, complex protein molecule? What about a living virus?
At what exact mass, at what exact physical scale does the shimmering probabilistic wave function finally give up the ghost? Where is the exact borderline where a system is too massive to exist in a superposition of states, and it is forced by the universe to collapse into a single solid reality?
There must be a physical threshold somewhere where the quantum magic fades away and the classical world takes over. But no one knows exactly where it is or exactly what triggers the collapse.
It is the ragged edge of modern physics, and understand the formulas we discussed today is the first step toward exploring that edge.
It makes you look at the mundane world around you a little differently. We have spent this whole time trying to master a diagnostic landscape that is incredibly complex and frequently counterintuitive.
We had to tear down the comfortable, predictable vending machine of classical physics, and we had to build something much weirder. But ultimately, we built something much truer.
You now have the mathematical muscle memory and the physical intuition to navigate those muddy waters. You understand not just what the formulas are, but why they exist.
You absolutely do. Thank you for joining us on this massive, intense deep dive. Good luck on your exam. Stay sharp on those units. And just remember, when you are staring down a terrifying alphabet soup equation on that test, behind all the complex calculus, it is just a wave trying to find its place in the universe.